The construction of a rocket engine test bench in a space complex requires several certifications, not only for the engine, but also for the equipment, instrumentation, mechanical and electrical devices and components, pneumatic systems, hydraulic systems, and the space facility itself. Firstly, we must take it into account the methodology to be considered for the development of test benches, which might vary according to the researcher, research center, company, or government regulations. So the following methodology can be proposed. Product concept, research, conceptual design, final design validation, computer-assisted validation, manufacturing and assembly, quality and testing, certification, official launch, commercialization. For the space launch systems, 13 rocket engines and approximately 20 turbopumps were required. Similarly, for the Union Soviet Energia rocket, 100 test engines were required. There are different types of tests carried out for the construction and successful launch of a rocket, of which the following can be listed: scale models, numerical simulations, ground testing, experimental flight testing, cold testing, and hot testing. In this presentation, what is interested in explaining are the ground tests, which can be performed sequentially or in parallel. Sequential or serial testing indicates that each main component of the test bench must be tested, and one cannot be tested without completing a previous test of another component. On the other hand, in parallel testing, multiple components can be tested simultaneously, optimizing time. For countries without experience in test bench setup, it is always recommended to start with sequential testing to avoid handling too many parameters at the same time. Both types of tests should consider cold and hot testing. Cold tests indicate that components and equipment are tested without combustion in the engine, while hot tests require the engine to be ignited for testing. Test benches are classified according to the placement and testing method of the rocket into horizontal and vertical test benches. Likewise, as mentioned before, test benches can be used sequentially or in series and in parallel. The debugging parameter is the ratio between the time of operation in a test bench with n number of tests and the time of operation in a flight test. The debugging parameter indicates that the higher its magnitude, the less time experimental testing is required. The more time spent on ground testing, the less time needed for flight testing. This simplicity shows that fewer prototypes need to be built for real-world testing. For example, if the magnitude of the debugging parameter is approximately 3, around 130 engines will be needed to validate the final prototype. However, if we increase this parameter to 5, the number of engines reduces to approximately 80. There are many systems that must be designed and tested separately and together in a rocket engine test bench. This presentation will only provide a brief overview of 3 of them. Out of 100% of the test bench tests, 15% are for the verification of fuel lines, fuel pumps, and their seals. 50% are for verifying oxidizers lines, oxidizers pumps, and their seals. 20% are for verifying the gas generator, and the remaining portion is for verifying valves, structures, leaks, tanks, secondary effects, etc. There are different pumping systems in liquid fuel rockets. Within the real prototype, we can observe in the following image the open cycle system. The turbine 4 is activated through an electric drive, and the supercharging system pushes the fuel components from above, which pass through the turbopumps 6 and 7 and increase the pressure. Part of the fuel goes directly to the gas generator, where controlled combustion is initiated, and the gases from this device directly impact the turbine, activating this component and moving the turbopumps. The combustion gases exit to the atmosphere through a duct 8. The fuel components are injected into the combustion chamber. Depending on the type of cooling systems, the fuel can be injected from the nozzle skirt to the head, or directly. In other configurations, the gas generator takes the fuel components from the tanks. Much depends on the designer and the country where the engine is manufactured. Let's now explain the configuration of the closed turbine cycle, which is very popular and regularly used by the company SpaceX. The turbine 4 is activated through an electric drive, and the supercharging system pushes the fuel components from above, which pass through the turbopumps 6 and 7 and increase the pressure. Part of the fuel travels directly to the gas generator 5, where controlled combustion is initiated, while all the oxidizer goes directly to the gas generator, and this is the main difference. The gases from this device directly impact the turbine, activating this component and moving the turbopumps. The combustion gases are injected into the combustion chamber. Depending on the type of cooling system, the fuel can be injected from the nozzle skirt to the head, or directly. The pumping system depends largely on the decisions of the chief constructor, economic factors, technical feasibility and viability characteristics. Therefore, this section presents construction and coupling proposals that can be employed. If any modification is desired to optimize the performance of the system in question, there are no limitations preventing its implementation. Firstly, it should be noted that in liquid fuel rocket engine, two main fuel tanks are considered. In the majority of carrier rockets, liquid oxygen and liquid hydrogen are used, or kerosene may be employed. However, there can be other successful combinations of fuels and oxidizers, such as liquid methane and liquid oxygen. This image displays a pumping system in test benches in an open cycle, and it is valid to use a separate fuel cooling system. This simplifies hot testing, but care must be taken to ensure similar conditions to flight conditions. The independent cooling system typically using water and can provide more effective heat transfer. The supercharging system 19 activates the flow of the pressurized gas, which enters the tanks 4 and 5 and pushes the fluid downwards. The electric start 20 breaks the inertia of the turbine 21, which in turn activates the turbopumps 16 and 17. The fluid then passes through a flow control valve 10 that is activated by a regulator 9 and monitored in a control room. Any impurities that could harm the turbopump blades are filtered 11, and then the flow rate 15 entering the turbo machinery is measured. A check valve 12 is in place to prevent the fluid from returning to the tank, avoiding unnecessary mishaps. At the outlet of turbopumps 16-17, a pressure sensor 13 is installed to divert a portion of the fluid to the gas generator 80 and the rest directly to the engine 1. Before entering the engine, a drain valve 7 is placed to handle any pressure disturbances in the combustion chamber, and a flow control valve 10 is used to carry out the test. Before discharging the combustion gases of the gas generator, a gas filter 22 and a drain valve are installed. The drain valve will only be closed when the test bench is not operational. For the placement of pumps, the diameters of the tank's inlet and outlet should be taken into account. This information can be used to determine the diameters of the connecting pipes, the dimensions of the pump for placement on a base and its mass. The choice of a pressurization pump will consider factors such as the density of the pumped liquid, the required quantity, the desired pressure, the mass flow rate, and the inlet and outlet pressures. The inlet velocity is recommended to fall within the range of 5 to 15 meters per second, while the outlet velocity should not exceed 30 meters per second. This helps to prevent cavitation phenomenon. There are many operating parameters in turbopumps that need to be considered when designing this component. These parameters are displayed on the screen. Due to time constraints, I will list them briefly, and the resulting turbopump design will depend on these parameters. In turbopumps, a screw system or helical pump tree is often installed before the fluid enters the centrifugal impeller or blade. This system consists of a finite number of blades and is used to increase the pressure before reaching the centrifugal turbopump. Its purpose is to prevent cavitation, which is a significant failure factor in liquid fuel rocket engines. The supercharging system depicted as a block preceding the fuel tanks. This system is a complementary part of the main pumping system, as it injects pressurized gas into the fuel tanks to initiate the pumping of oxidizer and fuel into the main supply line. This ensures a constant flow of working fluid, preventing tank collapse, reducing cavitation phenomena, and maintaining a steady flow of fuel components. The supercharging system creates a pressurized cushion on top of the tanks, and the design pressure needs to be maintained consistently. Therefore, this system must operate in a stationary manner, ensuring a constant and stable pressure within the tanks. The supercharging system consists of several components, such as gas regulators, different types of valves, pressure sensors, temperature sensor, and measurement instruments. The system can be classified as either continuous action or pulsating action, depending on its operation mode. Due to the time constraint of this video, I will only explain the second one, the pulsating action scheme. The pulsating scheme differs from the continuous one in that the gas tanks are pressurized at much higher level. Additionally, the pressurized gas passes through a pressure-reducing valve 12 and then goes through a series of electro-pneumatic flow control valves 3 that open periodically with the help of pressure switches or relays that are electromechanical pressure-sensitive devices or switches that function to open or close valves based on predetermined pressure. Subsequently, the fluid passes through a flange, then reaches the check valve 6. After passing through a filter 7 to remove any possible dirt, the pressurized fluid is injected into the fuel tank 10 to start the engine. The pressure and temperature of the gas at the inlet are measured using sensors 8. There is also a relief valve 9 that drains any excess pressure in a controlled manner through the control panel. Additionally, there is a safety valve 11 that automatically depressurizes the system in case of danger. As shown in figure, after the pressurized tanks 1, the supercharging supply line is divided into 2, and in turn, the first one is subdivided into 2 lines, resulting in a total of 3 supply lines before reaching the check valve. All 3 lines are equipped with pressure and temperature sensors 8, and each line has a pressure switch. If the pressure exceeds the set value in line 1 or 2, pressure switch 3 is activated, and the excess pressure is released through a brief opening of a pneumatic valve in line 3. This scheme is more reliable in operation and is commonly used in ground test benches for rocket engines. In test benches, the supercharging system has a different configuration compared to what was seen earlier in a rocket. Here, 2 types of supercharging system are used for test benches. The first one, gas supply system with compression unit, and the second one, gas supply system with cryogenic gasification. Water is injected through ducts that act as nozzles. These nozzles accelerate the water jet, cooling the gases that flow directly to the deflector area. The placement distance of the water jet, DCH, ranges from 1 to 1.5 times the diameter of the nozzle outlet, as recommended. As mentioned earlier, it will take a lot of time to explain each system in a test bench. However, this video provides an introduction to the systems found in a rocket engine test bench and their regulated construction. It should be noted that the characteristics of the systems shown here were not discussed. So for a deeper understanding, please consult the bibliography. Thank you.